Let's begin the notes with a review of the learning targets from the previous two sections. I can define and solve for kinetic energy. Remember, kinetic energy, we said, is the energy of motion, and it depends on mass and velocity. The formula for kinetic energy is Ke equals mv squared divided by 2. I can define and solve for gravitational potential energy. GPE, we said, is when you lift an object, you do work on it. You use a force that is against the force of gravity. This transfers energy to the object and gives the object gravitational potential energy. The formula for this is GPE equals weight times height. I can list and explain other forms of energy. There were 6 other forms that we discussed. The first is thermal energy, which is all kinetic energy due to random motion of particles that make up an object. Chemical energy is the energy of a compound that changes as its atoms are rearranged. Electrical energy is the energy of moving electrons. Sound energy is a wave of vibrating particles of air that vibrate your eardrum. Light energy is produced from the vibrations of electrically charged particles. Nuclear energy comes from the change in the nucleus of an atom. We said there were 2 types of changes, fusion and fission. I can explain energy conversion. Energy conversion is a change of one form of energy to another. Remember, we said that any form of energy can change into any other form, and sometimes they change into more than one form. The learning target for today, I can define the law of conservation of energy. Section 9.3, Conservation of Energy. Let's start with an example. Let's talk about roller coasters. Where does a roller coaster get its energy from? When I press play, the roller coaster will begin on the left side of your screen and travel along the tracks all the way through to the right side of the screen. While it is playing, there are 2 things I'd like you to watch. I'd like you to watch this area here, as it will become a pie chart showing you the differences between potential energy and kinetic energy, as well as checking out the velocity of the roller coaster as it's going. Let's go ahead and play it through once. The pie chart pictured very clearly shows the differences in potential energy and kinetic energy throughout the roller coaster. However, it goes through very quickly. Let's do it in steps this time. Step 1, you can see the increase in potential energy. Moving on to step 2, you can see that potential energy change to kinetic energy. In step 3, there is a small amount of potential energy as we're gaining height. Potential energy once again increases in step 4, but there's still quite a bit of kinetic energy. Step 5, once again, is all kinetic energy as the roller coaster reaches the bottom of that second hill. Step 6 again shows a small amount of potential energy, but most of it is still kinetic energy. Let's take a little bit closer look and see what's going on here. Potential energy to kinetic energy is being changed as the ride is in motion. Some of that energy is also being transferred to sound too. Some is also converted into thermal energy because of friction. Remember, friction is a force that opposes motion between 2 surfaces that are touching. The first hill always has the highest energy. If you think back to the video we just saw, the pie chart had the most potential energy at the beginning of the first hill. Why is this? Roller coasters are a closed system, or a group of objects that only transfers energy to each other, the tracks, the cars, and the air. All energy transferred, added together, will equal the starting energy. The picture below shows another example similar to the video that we just saw. It shows again at point C that the highest potential energy is at the first hill. The law of conservation of energy states that energy cannot be created or destroyed. Every time you convert energy to another form, some of it is converted to thermal energy. The picture below shows this. Why? The answer is friction. Attempts to make machines that run forever without adding energy have been tried. These attempted machines are called perpetual motion machines. It is a machine that puts out as much energy as it takes in. The pictures below are two examples of proposed perpetual motion machines. Let's take a look at an example of two of these machines. This example is called an overbalanced wheel. This is another example of a perpetual motion machine. This second one is far more complex than the first. While perpetual motion machines are interesting, we have yet to make one that can run forever without adding energy. Unfortunately, both of the models that you have seen lose energy due to things like friction and sound. Energy efficiency is the comparison of the amount of energy before a conversion compared to the useful energy after the conversion. It's important to note that we are looking at useful energy after the conversion, or in other words, energy that can be used. Friction is an example of an unuseful energy that is often created. An example would be, how much bang for your buck? A car gets approximately 37 miles per gallon versus an SUV like the Hummer that gets 14 miles per gallon. One way that we have made cars more efficient is to change the aerodynamics. This has to do with the shape of the vehicle and the way that they move through air. This concludes the notes for section 9.3. In the next section, section 9.4, we will discuss energy resources.